Hey, this is Voxide and I hope you will enjoy this free chapter from my geometry-based simulation course in Houdini and Nuke. You can use the timestamps to easily navigate through individual lessons. For the full course and more details, check out the link in the description. Before we get started, and we will be creating everything from scratch, this will be how our final scene will look like. And let's just get a brief overview of what we're going to be creating and sort of break down the different phases of how this effect is laid out. So we will start with an Alembic animation that will be provided to you in the download content. And also I will be providing this entire scene, so if for any reason you get stuck at any lesson, you can always just refer back to this zip file. So over here we have our Alembic animation. So this will be the hand animation. We are going to create the main movement of the particle simulation on a frozen geometry. So we will choose a frame and we will freeze this geometry and create our movement on this geometry. And then we will update the simulated points to stick to the deforming geometry, and then we will cache this out. And just as a preview, this is how it will look like. So we will create the simulation here, and then we will just stick them to the points. And then you can see that the points sort of branch out from the tip of the fingers and they fly around in the circle, and we will be generating some curves to help us with this motion. So these are the curves that we will create for the motion. And if I template the frozen geometry, you can see that these curves start at the tip, and we will achieve this effect through various procedural methods. Over to the side we have a bunch of other helper geometry, which will be either be used for the direction of the particle movement and also to create some custom attributes for our points. And then after we cache the result, we will set some color attributes, and we will split the stream into one stream that will be the emissive points and one stream that will be the smoke points, and render these separately. So in our first lesson we will start from this Alembic node, which is just going to be our animation, and work our way down from there. So let's get started and drop a geometry node, and we can rename this to FX. Doesn't really matter what you name it. And let's just drop an Alembic node. And then we can, in this file name, we can load our hand animation. So this is what you will download with the contents. Right, so let's set the load as unpack Alembic delayed primitive. So this will allow us to access the polygons and the points. So if we set this to default, you can see that this is just one full object, sort of. Anyway, just set this to unpack. And let's go ahead and create an attribute VOP. And we'll name this set emission. Right, and if we dive inside, we want to generate a noise that goes over all of these points. And actually, let's go up one step, and we forgot to freeze the animation like we said in the overview at frame 90. So this is the geometry that we want to work on to create our particles. So in between these nodes, I will just drop a time shift, and I will Control Shift click this area over here, and yeah, just leave this as 90. Alright, so now the animation is froze at 90, and let's move forward. Let's go back inside this attribute VOP. And we want to use a flow noise, sorry. So anti-alias flow noise, and we will just plug this into the CD to visualize it. And right away, let's just right click and go to VexVox VOP options and create input parameters. Alright, so now we exposed all of these noise parameters, and we can go ahead and play around with the frequency, amplitude, offset, and all of that stuff. Alright, let's go ahead and create a simple animation, and we can use the offset for this or the flow. Let's just use the flow, I think. So if I just type here $T for time, and now I scroll the animation, we can see how this will work. And so this depends on your preferences. Maybe this is a little too fast for me, so I'll just drop this value in half, so I can just divide by 2. Alright, so now this is twice as slow. Cool. Let's move forward. and let's fit this noise, and I'll drop a fit range in between these nodes, these values here. And I sort of want to normalize the noise, and for AA flow noise we can set the source min and source max to -0.5 and 0.5, and now this sort of gives me a scale of 0 to 1 for the noise. And I'll drop, so this fit is just to normalize the noise from 0 to 1 sort of, and then this second fit I can plug this in, so we can middle mouse click this first value here, so src min and promote parameter, and I'll double click this handle, and let's just name this to threshold. Alright, so this will be used to control the appearance of the noise, and you'll see in a second. And we can also promote the second value over here, so promote parameter, double click, and let's rename this to width. What I want to do is link the width to this to the threshold value. So if I grab this wire here, I can now add an add node, and I can simply link the first threshold value to this add value. Alright, so what will this give us is, if I go up here at the top level, there's going to be a threshold and a width. So if I turn down the width, you can see that this will increase the contrast of the noise, and we can now animate this from 0 to sort of around 1 to create, or rather to make the noise disappear. Alright, so we can play around with these values, and maybe I can just turn on disable lighting, maybe increase the frequency a bit. Alright, so let's say that this is how my noise will look initially. Maybe just drop down the frequency a bit, and I can now animate this threshold value. So maybe I want our emission to be emit 50 frames, and then from frame 50 I will hold down Alt and left click this value. This will add a keyframe. You can see the green keyframe over here, and let's move forward maybe to around 90. And now I will slowly fade this over time until everything is completely black. Alright, so I'll just increase this to all the way up to 1. So now as our points get darker, they will stop emitting particles, and the particle emission will stop entirely at frame 90. One other thing that I want to do here as well is what I want to achieve is have the particles sort of start only halfway on the hand, and then they slowly move upwards towards the finger. So we don't really want any points or particles spawning over on this side here. This is completely optional. You will achieve the same result either way, but we might as well do this and make it a little bit more interesting. So the more interesting your sources will be, the better your overall effect will be anyway. So let's go back here, and we want to, I'll just hold Alt and drag this over, and we can generate a new node for our geometry global parameters here. And I'll just grab this P value, and let's look for relative to bounding box. So then I can split this into, so if I go vector to float, I can split this in 3 vectors, and we are looking for, if we look down here at the bot, we can see that we're looking for the z-axis, which is the third value over here, and I'll just plug this into a ramp parameter, and I will multiply our noise by this value. So I'll multiply and multiply it with the ramp, and also I'll set this ramp to be spline, and if we go up a level we can adjust the ramp, and you can see how this fade effect is going. And I'll just turn around the points, and we can adjust now the ramp. Alright, so this is sort of like limiting where our particles will spawn. Then finally we can add a rest, and this will come in handy later, and I'll explain this when we get there. And I think this is pretty much it for our geometry source, so we can drop down a null just for the sake of cleanliness, and I'll just type this out source, and then next we can drop inside the PubNet. So now we can set up a simple pop simulation, and I'll just go ahead and type pop network, and I'm holding down shift and enter, and then this will automatically link with the latest node that I create. So just type just hold down shift enter to link up the node that you want to create. Alright, so if we play this, we can see that it's emitting where we have the color, but actually it's emitting everywhere on the geometry if I template the points or if I display the points, so you can see. And we have to fix that, so let's go back and let's step inside the PopNet. And for my source, let's go ahead and turn off the guide. And for emission attribute, I will leave all of these as they are, and emission attribute, I'll just type here CD. Alright, and a very important step here is to check scale point count by area. And this is what will allow us to only emit where we have some color information, or rather when the color attribute is above 0. So I'll set this to 1 for now, and if we preview this now, you can see that this is now working properly, and if I display the points, it's only emitting wherever there's color. Alright, pretty cool. In birth tab, I can set the life expectancy. Let's set this for now to maybe a value of 6. And for life variance, I'll just copy paste this parameter. So copy parameter, and then I will right click and paste relative references, and I will just divide this value by 3. So now the life expectancy will be 6 and a life variance of 2. Alright, so now our particles are currently lasting 6 seconds, and we will increase the birth rate later, and that's pretty much it for this pop source. And so now we can move forward. Before we continue with our PopNet setup, we need to set up some attributes on the geometry to help us along the way. So let's go back up a level, and I will create a null here where our time shift happens. So this will be just our geometry. So I'll just create a null, and I'll just name this to maybe frozen geo. Alright, and I will Control C to copy this, and I'll just type object merge and merge this over here. And let's rename this to geo and drop down an attribute VOP. Alright, so this whole thing is exactly like saying it would be like just placing this over here, but this gets convoluted easily, so I don't really like to branch out from one node into another part of the scene. So my preferred way of working whenever I have to like draw out a long wire from one place of the scene to another place of the scene is just using an object merge. So I'm just merging this over here, and then I can just place these wherever I want, and this will just keep the whole scene a little bit more organized. Alright, so this will be the attribute VOP, and this will be set direction. Alright, so just set dir. Now if we look at the geometry, the direction that we want really is just a vector that goes from over to the end of the hand over to towards the tip of the fingers, right? So it's something like if and you don't have to do this, this will be just an example. So if I just create a parameter here and name this to dir, and let's create a 3 floats parameter, and maybe increase the parameter window over here. And to preview this, I can just set this to be the n and move up a level, and I'll set this to be a value of 1 in the z direction. So here is 1, and I can preview this. This is kind of the direction that we want, so we want the particles to also move up along the hand while creating the swirly rotations. One problem here is that I really want this upwards direction or the along the hand direction to really follow the finger. So we can see that for the thumb, for example, this attribute is going straight forward, whereas we really want the direction to go along the finger like so. So we want this direction here, and for this finger all of these fingers are slightly offset, so we want the direction to go like this and like this and like this. So we want them to respect the orientation of the fingers. So setting this direction attribute to be a constant value of 1 along the Z is not quite sufficient. So let's go back inside and I'll just delete this attribute. So what we will do here is create curves inside this geometry that each represent a direction of the finger. And I'll show you what I mean. Hopefully this will make sense in a second. I will template this attribute VOP and I will go ahead and create a curve object, and I will set the render flag to this. And in my top view, so if I hold down space and press 2, I will go in my top view. Make sure that this curve is set to NURBS curve, and I will press enter inside the viewport and I can simply draw out our curve. So I'll do 1 point at the top of the hand and maybe 1 point over here, another point here, and then here. And now I can middle mouse button to exit this curve creation mode. Alright, and if I press space, if I hold down space and press 1, I can go back in my viewport and I'll just hit escape to enter the editing. And we can see that this will be our curve, and we need to create some slight adjustments. So I'll press enter again, enter curve mode, and with the new curve tools in Houdini 19, now I can press F and this will enter the editing mode, and we can just grab the points and just move them into position just so it follows the finger shape exactly. Alright, so make sure that the curve is roughly inside the center of our curve geometry, and now this should be fine. So I can do this now for all of these other fingers as well. So I'll just hold down Alt, and with my left click I will just drag this over to create a duplicate, and I can simply move this into position for my second finger and just make sure that this is inside the geometry. So this might take just a little bit of tweaking. And I will basically repeat the process for the rest of the fingers as well. So Alt and left click, drag. So for the thumb, I will create a new curve node. So just type curve and make sure that this is set to NURBS. And I'll press spacebar 2 for my top view and make this the render flag. Press enter and I will just draw my curve. Alright, and I can press escape and then spacebar 1, press enter again and F to enter the edit mode, and I'll just move this into place. Alright, and now if we add up all the nodes, so I'll select all the nodes, hold down Alt and drag a wire, and this will now automatically merge all of them. And if I press escape, we can see that this is what we end up with. And don't worry if it's not perfect. It doesn't really need to be exactly like mine. It just needs to, this is just to roughly get the overall direction for our points on the geometry. So I'll just arrange this slightly and maybe drop down a null and set this to be curves direction. And actually before this null I will need a resample node, so I'll type resample and let's preview, and let's say that the default value of 0.1 for the length for this resample will be fine. And let's remove now the template geometry, so I'll just left click this. And one other node we need here is going to be a polyframe. So if I just type polyframe, let's add this and let's template this. For my points, I'm gonna set the style to first edge and I will disable normal name, and the tangent name attribute is what I'm after. So I'll just name this to dir. And if we hover over the node and press this I, we can click on this dir to create a visualizer, and we can see the direction of the vector. Currently it's going in the opposite way, so it's going like this, but we wanted to go the other way, so we can just simply add a reverse node before the polyframe. So add a reverse, and now we have the direction, and we can move forward. Let's actually go back to this polyframe node and let's rename this to dir with all lowercase. So there's no need to make this D capital, just because it's gonna get so easy to misspell later down the chain. So just make all the letters lowercase, so we end up with dir. And if we right click the visualizer and go to edit, we can just set this to dir. Right. So this will be a lot easier to avoid misspelling it later. Alright, so we can grab this geo and the attribute VOP that we created initially, and I'll place this down below, and let's use an attribute transfer between these nodes, and we will just transfer this dir information. So if I preview this, we can turn off the primitives, and for points I just want the dir. We can now use an attribute blur, and this will just smooth out this direction vector that we created. So if we go to our blur, and for attributes I will type dir and remove pin border points and set this to proximity, and I'll just increase the iterations. Alright, so now this will just create a smoother transition between all the directions. And so we can see that we have a direction that we want, which is going along the fingers and along the hand, and we also want the particles to go around the hand. So the way we can create this is by using a cross product between two vectors. And in case you're not familiar with the cross product, I'll just turn off the visualizer for now, and let's turn off the template points. And in order to explain this cross product a little bit better, I'll just create a simple sketch to illustrate this. But really, if you know what the cross product does, then it's safe to skip this part, but you might as well watch it. So let's just create a screenshot here. And I'll go over into Photoshop and create a new project. Paste this, create a new layer. So currently we have for each point a vector that goes along the finger, right? So this is the vector that we created. Now we want a vector that goes around the fingers, right? That goes like this. And essentially what the cross product does between two vectors is, if we have one vector that's going in this direction and another vector that's going in any direction like this, you can imagine that the cross product is simply a vector perpendicular with an imaginary plane that these two vectors create. So if I were to sort of draw this imaginary plane, it would be something like this. So you can imagine that the cross product between these two vectors is going to be the vector that's going perpendicular to this plane over here in this direction. Only of course this vector is going to have the origin on the point itself, so somewhere around here. So this is sort of like the cross product. So if we go back to our case over here, in order to get this vector, we can sort of do this in reverse, and we can determine that let's see, this will be the plane, and the vector that we need for the cross product is going to be this vector over here. So now this vector with this vector, which is the dir, will create the vector that we're looking for. And this vector, as it turns out, is simply our normal vector, right? So we already have this. So we have our normal vector and we have our direction vector, and we can create this new vector that we're looking for, right? And let's just grab another point here, because the normal changes per point, right? So the normal for this point will be this vector over here. The direction vector stays the same, going in this direction, so this is the direction vector. And then these, you can imagine the plane that this creates, and the perpendicular vector will be this. Well, let me get the red to be consistent. Alright, so now each point will have this direction vector that is going around the fingers like so. using our normal and the direction that we created. Right, so simply imagine a plane, and then the vector is going to be perpendicular to this plane that the vectors create. So this is the cross product. So now if we go back in Houdini and we go inside our attribute VOP, we need to import our direction vector that we created. So I'll just type bind and make sure that this is a 3 floats and type in dir. And we will also export this after we create the cross product. We'll just export this to the dir. So we will just be sort of updating this vector. So I'll just type bind export and three floats and dir. Right, so if I plug this in, nothing changes. We still have the same old dir that we created. And now if I add a cross product here, and for my second vector, I'll just plug the normal like we talked about. We can see, let's actually go to the dir and turn on, rather rescale this. We can see that we create this swirly vector that we were after. So whenever you create a cross product, you usually want to normalize the vectors that you're using. So let's normalize both of these, and these will just ensure that they're both a scale of 1, so that the cross product will be a consistent value for all the points. Okay, so now the direction that we generated is simply going around the hand and around the finger, so each finger is individually. And in the case of the thumb here especially, this is why we generated the curves to create accurate directions. So for example, if I were to use, and you don't have to do this, so if I were to use, let's actually just set a constant, and 3 float constant with a direction of z. So if I were to use just a simple direction on the z and use this as a cross product instead of the direction that we generated, you can see that we kind of get the same result. So it might not be noticeable here around the hand, but the fingers are slightly not following, or rather the direction is not following the orientation of the fingers, and this is especially apparent here in the thumb. So you can see that with our direction that we created using the curves, if I plug this in, you can see that this is much nicer and a lot more consistent with the orientation. Alright. One problem we have here is that if we want to use this direction as it is right now, it will flow around the fingers, but I also want it to flow along the hand as well. So we need to bring some of that original direction that we created in, or rather back in. So we can use a mix node here. And if I grab this normalize, so this is the original direction, so I can just grab this normalize and plug it into the second input. We can now control exactly how much it swirls and how much it flows along the hand. Alright, so we can see that as I change this value, we get like we get no swirling, and as I decrease this, we get more and more swirling. So we want this value somewhere around the middle, and we will actually just right or rather middle mouse button click and promote parameter, and double click here and just name this to, I'll just name this to bias. So now if we go up a level, we can control exactly how much swirl we want in our motion for the particles. So we can create a null and name this to dir. And I'll just move all of these, let's see, over here to the right. And we can also press Shift O and just encapsulate these nicely. So this will be our direction geometry. Okay, so now we have our direction geometry, and back inside our PopNet, we can dive inside the network and we will create a PopVop node. And essentially this is like an attribute VOP just for particles. So the difference here is that whatever is inside this PopVop will be updated every frame. So that's an important difference. Now let's go back up a level, and the way that we can make this PopVop communicate with the outside geometry is if I go back up a level one step, I will just grab this dir null and I will press Ctrl C to copy and go back inside our network. And for the PopVop, there's an inputs tab over here. And for input 1, I can set this to be a SOP source. And for the SOP path, I will just Ctrl V to paste our geometry object. So if I go inside this pop-up, we can access the geometry that we created from this op input 1 value over here. So now we want each point of this particle simulation to look at the closest surface on the geometry, so on this geometry over here, and grab the direction attribute that we created earlier and update the velocity by that attribute. And the way we're gonna accomplish this is by using the XYZDist function. So if I grab this wire over here and press tab, I will search for XYZ distance. And we can see that this function outputs 3 parameters, and we want to use the position based on the position of the point. Let me also create a quick sketch, and maybe I can illustrate this better. So I will go up and I will template the geometry, and let's just zoom in over here, and let's just create another screenshot. And what XYZDist is gonna do is, for example, if we have a point in space anywhere, let's just say that we have this point. So we have the particles, right? We have a bunch of particles, and for each point it's gonna do the same function. So let's just solo out this point. It's going to find the shortest distance to the geometry that you give it, right? So it's going to search in an infinite radius, and you can actually specify the radius. Let's go back here inside. So you can specify a radius here. You can see that there's a max search distance, and by default this is a crazy value here. So this just basically means infinite. So just look outside of the point that you give it into an infinite radius. And when it intersects with the geometry, so let's say that it falls somewhere around here. Now this will give me a distance, so this will give me a value, and let's say that maybe, let's actually just go on the other way. This will give me a distance value, right? So let's say that maybe this is 0.23, which will be this dist over here. And it will also store the number of the primitive that this hits. So this primitive over here, right? Let's say that this primitive has a number of 54. It doesn't really matter the number exactly, we just want to store the value. So this will be this value over here. So this is the prim, will be an integer value. And then finally we have prim uv, which will be a parametric coordinate on where exactly on the primitive this hit. So we can imagine if I laid out this geometry over here to the side in a 0 to 1 space, so this is this geometry. Each primitive in Houdini, so each primitive that's creating this geometry, has an intrinsic 0 to 1 UV coordinate system. So we can imagine that we place all of these polygons in a 0 to 1 space, 0 to 1 and 0 to 1, and wherever this point hits, it's going to give me the coordinates for that. So let's say that in the 0 to 1 space, this point hits somewhere around here. It's just going to give me the coordinate for this point. So we can sort of like draw some imaginary coordinates here. So this might be 0.4 on the V coordinate and 0.9 on the U coordinate, right? This prim UV attribute is specific for each polygon individually. So this is a special intrinsic attribute that Houdini has for all the primitives that are contained within an object. So it's not the same as the regular UV coordinates that you're used to working with other software. So this is basically what XYZ distance does. It's essentially kind of the same as a PC Open. The only difference, or rather the big difference between PC Open and XYZDist is that PC Open does pretty much the same thing, right? Only it's looking for the closest point on the surface. So PC Open will grab this point and will find me the closest point on the surface, right? So it can only go from here to here or here or here, so it will only look for points. Whereas XYZDist will consider the entire surface of the primitive that it intersects with. And so what we're going to do with this is that we are going to use this information, so the number of the primitive that it intersects with and the UV coordinates of that primitive, to grab an attribute from the geometry. And the attribute that we're going to grab is going to be this direction that we created. So let's imagine that this is sort of like the direction that we created for all the points. And the beauty of XYZDist is that it's going to grab the interpolated value of all these points. So let's say maybe that the direction attribute for this point is going this way, and maybe the direction for this attribute is slightly off, so it's going this way, and then this one is going this way. This is going to grab the interpolated version of all of these point attributes, right? So it's going to give me this. And when the point will update its position, so let's say that it's going this way, and now my point is over here, and now the current position that this will fall on, the surface of the primitive, is going to be here. It's going to again grab the interpolated result of all of these points. So it's going to give me a smooth, consistent direction. So this is why I prefer using XYZDist instead of the PC Open, just because it creates nicer and smoother results. So now back in Houdini, we can grab the primitive attribute that we are looking for. So if I drop down a primitive attribute, we can see that for the file we want to use the same OP input 1. So this will be the geometry that we created earlier that contains our attribute, and the attribute is going to be dir, and this is a signature vector attribute. We are not going to be using this distance, so we don't care exactly how far apart these are. We do care about the primitive that this point will intersect, right? And primuv will be exactly where on the primitive this intersects. So now basically any of this point will look at the geometry that we created, and it's essentially going to borrow the direction attribute that we created, and we will just plug this into the V. And now if I press play, we can see that we get a swirly animation. Now you can see that the particles are sort of drifting away from the surface, and we will fix that in the next lesson, but for now this is what we are looking for. And we can drop a multiply between these nodes over here, and I can promote the parameter, and we can name this to speed. And now if I go back up a level, we can set the speed maybe to 1.5, so this will be 50% faster. Alright, but obviously you can use whatever speed value you want. So this is the motion that we're looking for. And of course we can also go back to our geo that we created, and we can see, let's take a look at the dir attribute over here. And we can maybe make this go a little bit more along the geometry. So adjust this dir just a bit, maybe let's say 55. And let's go back, and here we have it. And let's take a look in the next lesson to how we can stick the particles to the source geometry. So for this lesson I want to showcase one approach that we can have to making our points stick to the surface geometry, and this won't be the technique that we're going to use ultimately, so you can go ahead and skip this lesson if you're not interested, but I highly recommend that you watch this anyway. But you don't have to follow along with this lesson. So one way we can do the sticking points to the surface is if we create a pop wrangle over here. Alright, and we want to grab the geometry from the outside, so let's step a level outside, and I'll just grab this geo over here, so this is just the geometry. I'll press Ctrl C and go back in our pop wrangle, and for the inputs, for input number 1, SOP, I'll just paste the geometry, so now we can access it inside this pop wrangle. And the code will be, I'll set the position to be MinPos 0 and at P. So what minimum position will do, MinPos, we can see here, it finds the closest position on the surface of the geometry. So it finds the closest position, and then I'm setting its current position to be that position. This is essentially what a ray node will do. And if I play this, we can see that it sticks to the surface. So why we're not using this method is it creates some unwanted stepping between the particles, so the movement of the particles. And this becomes more apparent if I set the birth rate here to maybe something higher, so 50,000. And if I play this back, maybe it's still not that apparent, but we can kind of see some stepping, some ugly stepping happening in certain areas. And if I increase this even further to, let's say, 500,000, which will be close to the final count of the project. So when you're working with millions of particles, you can already start seeing right over here this very nasty stepping, which can be overlooked, especially if you're going to use motion blur in the final results. So this MinPos method is decent. It does the job, but we have a better method. It's just a little bit more complicated, and it's using volumes. But you know, if you want, if you're gonna find the method that we're using too complicated, you can also use this method as well with the MinPos. So I just want to let you know that this is the reason why we're not gonna use this simple method with the MinPos, is this nice nasty stepping that's happening when we increase the particles. So let's move forward and start from the beginning with the sticking to the surface and use the actual method that we're going to be using. So in order to use this other method, we will be needing two functions. One will be volume gradient and the other will be volume sample. And to explain these functions, I will first create an SDF. So we will need an SDF. So let's grab this geometry that we already have, and let's copy paste this and just place it over here in a separate chain. And let's type VDB from polygon. So we want to turn this into an SDF. And for voxel size, let's maybe use something 0.25 should be good. And the voxel size, it's important, so this is how accurate the particles will be sticking to the surface. So something like 0.25 should be good. Now for exterior band and interior band voxels, let's use world space units. And let's fill interior. So we want all of the interior of this geometry to be filled with voxels. If I drop down a VDB visualize tree, we can see the individual voxels that create this SDF. Alright, and essentially if I template this node and I go to my PopNet and I let it play for a bit, we can see that we have a lot of points that sort of step outside of the bounds of this volume. So we need to go to our VDB from polygons and increase the exterior band and maybe just set the value of 1 over here. So this will just ensure that any stray particles that are swirling too further apart from the geometry will be caught by our volume. Alright, so we just set this exterior band to 1. Let's go back here to my visualize tree and let's actually disable this. And let's just work on one point. So this part you don't have to follow. I will create this specifically for demonstrating what we're going to be doing inside the PubNet. Let's just create an add node and let's create a point, and I'll type enter. I'll press enter in the viewport and I'll just move this over somewhere around here maybe. And I'll also turn this back to points. And if I preview this, let's maybe press D and I'll go to guide and let's go to geometry and just make the point size bigger. Alright, so we have our geometry. We turned it into polygons, and let's template this back. Let's turn on the visualize tree back. Let's template the geometry and let's go in a side view. So I'll just press space and 4, and so this will be a side view, and this is a lot easier to digest the individual voxels and what we're going to be creating. So if I also grab this point now, we can template this as well. So we'll template both the geometry and the visualize tree and our point. So now I can just drop this in Photoshop so I can do some drawing over it. So this point over here will be just one point of our whole particle simulation. And let's start with a volume gradient first. So let's type volume. This will be the volume gradient function. What this does is it's going to sample a position, and in this case it's going to be the position of the point, and it's going to look at the volume that we give it, so in this case this whole volume, and it's simply going to give me sort of like the normal of the volume. So the volume gradients is going to give me a direction based on the increasing value of the voxels. So a voxel has a value, an SDF in this case has a value of, so this voxel here, that's, let's say this is right on the surface, this will have a value of 0, and the further it goes inside the geometry is going to have a negative value. So this might be negative 0.01 and so forth until it reaches sort of like the center. And so going inside the geometry, the values will turn negative, and going outside of the geometry they will be positive. So this will be 0.1, so this is a negative, and maybe 0.5, and all the way up to the edges of our volume, which maybe this will be 0.7. So these are just estimates. And then what the volume gradient does is simply look at the lowest value and traces a vector to the highest value. And this will be a normalized value, of course, which will have a length of 1. So you can imagine that this volume gradient computes a direction that's going all over the place, something like this. So something like a normal of the volume, right? So maybe for a point that's all the way over here, our volume gradient for this point will be something like this, right? It's looking in the direction like so, going from the smallest value, which is negative some number, all the way up to the highest number, which will be a positive value. So now if we go back in Houdini, we can use an attribute VOP, and like I said earlier, you don't have to do this part. The only part that you will have to do is this one, and I will actually just use a null over here and rename this to SDF. So this part is relevant to the course, and this other part here will just be a demonstration. I'll plug this into the second input over here in this attribute VOP and dive inside and drop down my volume gradient. And for my sample position, I'll use this the position of the where the point is currently. And for the file name, I'll use the input 2 where we placed our volume, and I'll actually have to disable the visualize tree because we want to use the volume. And going back inside, the input will be second input. And if I just plug this into the normal and visualize normal, we can see that we have this volume gradient that we talked about, and as I move this point around, it will update with the position. So if I press D and go to guides, I'll set the normal to 1. So hopefully now you can see better. As I move this inside the volume, this will now point to the most inside point inside this geometry. Okay, and you can see that if I step outside of the volume, so it doesn't have any voxels nearby to find, we don't have any gradient. So this is why it's important to set the exterior band to a higher value. So you can even go, if you find your particles that are straying too further apart from the mesh, then you can just increase this exterior band property. So if we increase this to something like 2, you can see now that I have more room to place this point, and it will find voxels to create this volume gradient. And let's just set this back to 1 and set this point back to where it was roughly. So now to get this point to stick on the surface of the geometry, we can subtract the current position at which this point is currently with this vector that we found from the gradient. So we can step inside here, and I'll just grab the position and I'll subtract this vector that we found with the volume gradient. and if I plug this into the position, we can see that it roughly should it where it should be around the surface. It's just the problem is that this volume gradient gives me a constant value of 1, so this gives me a normalized n. The problem here is that all of the vectors are going to be 1 unit length, so if this will be 1 unit, right, and it's going to shoot it somewhere around here, and maybe if I have a point here, again it's going to grab the vector and it's going to be 1 unit, so this point will end up somewhere around here. We need a way to somehow rescale this vector, this gradient vector, just so that it's when we subtract the position, it's going to hit exactly on the surface. So we actually know how further apart this point is from the surface because the SDF volume gives us that value. So like I said earlier, the SDF has increasing voxel values to, outwards and inwards, right? So if there's a value of 0 right here in the where the voxel is nearest to the surface, then it goes upwards in value, right? So this will be 0.1 and 0.2, 0.3 and so on. So we can grab this value here and we can multiply our vector gradient, which is 1 unit length, with this value here that that we get from the SDF. So let's say that the voxel value for this point over here will be 0.3. If we multiply the 1 unit length vector by 0.3, we will get exactly a vector that's going from the surface to the point. And then when we subtract this vector, we will get the point to sit right on the surface. So this is what a volume sample will do. Basically, we have a point over here in this voxel. It's going to look at the voxel that it's closest to, and it's going to grab the SDF value for this. So maybe this is at around a value of roughly 0.7, right, in world space. And it's going to multiply the gradient vector by this, and it's going to give us a vector exactly that's going to the surface. So now back in Houdini, I can go inside this attribute VOP, and I will grab a volume sample, and again I will use the P for sample position and the output 2 for my file name. And actually we don't actually need to use the file name, we don't have to import this as well, we just set the input here to the second input. Okay, and we will multiply this volume gradient by the value of this volume sample, and now we can see that it's right on the surface. So if I were to bypass this subtract node over here and let's just update the normal and disable the subtract, we can see that if I were to, this is why we subtract, because if I were to invert this value over here with a constant of -1, this will now give me a vector that points directly to the surface. So no matter where this point is, it's going to give me the nearest point to the surface. And by using this technique, so I'll just go ahead and remove this. If by using this technique instead of the minimum position one that I showed earlier, we will get a nice interpolated smooth result and get rid of all that nasty stepping. So in the next lesson, let's apply this to our PubNet simulation. So now all we have to do is set this up in our PubVop inside the .NET. So let's go up a level, and I will just delete these nodes that we created for the demonstration and just keep the SDF volume. All right, and let's actually just grab this SDF null, and I'll Control C and go inside the PubNet and give it a second to load, and let's set this back to pixels. And let's create a new PubVop. So PubVop, and for the inputs, the first input, I want this to be a SOP, and I'll just paste the SDF over here. So now we can access the SDF from over here. So we're just gonna recreate what we did in the demonstration, which is I'll drop down a volume gradient, and I'll use the sample pose to be the P, and for the input I'll use the first input, and I'll also create a volume sample. So just take note that there are two volume sample here. So there's volume sample and volume sample vector. Since we are trying to access a float value, the simple volume sample node will be sufficient, and we'll just place the p for the sample pause, and we will just multiply these values now. Okay, and if I set this to the p, so we want to update the position rather than the velocity. So we have to use a subtract here. So subtract the original position of the points with this new vector that we create with the volume gradient and volume sample, and update the position for each frame. And now if we go back, and if I go in my perspective view, we can preview the animation. And I think we forgot one thing. For the volume sample, we forgot to set the input to be the first input as well. Okay, so now it sticks to the surface. And the whole reason we did this setup is to avoid the stepping of the particles. So let's go back in our pop source and increase the particles to, let's say, 500,000, and let's preview a few frames. And we shouldn't have any stepping happening. We should have like a smooth direction of the particles. And we can see now that there is no stepping occurring. And it's still computing pretty fast. Granted, these we are already working with a few million particles over here, and I'm getting some pretty decent playback results. Of course, this will depend on your hardware, but this is a pretty fast operation overall. Okay, so let's just set this back to maybe 5,000 or 50,000, and let's rename this to stick to surface. And back inside my original initial movement pop-vop, I will just want to add some noise to the movement of the particles. So we have the overall direction in which we want the particles to travel, and we can add some noise simply by adding some curl noise. So we will just grab this geometry VOP, and I'll hold Alt and copy it over. And from the P, I want to generate a vector to vector 4 node, and this will give me a vector 4. So now I can also use this noise, or rather this vector 4, to generate a noise that evolves over time. So I will just plug the time inside the fval4 over here, so the fourth value, and let's plug this into a curl noise. Okay, and this curl noise I will simply add before we plug in our initial direction inside the V. I'll just set an add over here, so after the multiply, and add the noise. And if we play this back, we should see now we have a lot of swirly motion and a lot more interesting effect. This is a little bit too much. Let's go to our time here, and I want to, well, actually I will promote the frequency, the offset, amplitude, roughness and attenuation, and maybe turbulence as well, and maybe the type as well, and go up a level, and we can now access all of these settings from our pop-vop over here. Okay, and let's take a look. The first three values for the frequency will be for the position, so I will just link these all together. So I will copy parameter, right click, paste relative, right click, paste relative, and the fourth value here, this will be how fast the noise will evolve over time. So maybe I will just set this value to 0.5, so the last value, and I'll drop down the amplitude maybe to 0.6, and maybe less roughness, maybe 0.4. And if I preview this now, we can maybe increase the amplitude to 0.8. So because we drop down the roughness, we need to increase the amplitude. So this amplitude and roughness value kind of goes hand in hand. Okay, so that's looking pretty fine. And for example, if I want the noise to sort of evolve faster, I can set this to a higher value of 50. And this is just to illustrate what this last value over here will do. All right, so you can see that now it's moving a lot faster, and it's very chaotic and sort of feels a little unnatural. So maybe actually just drop this to a value of 1. Okay. So we want to maintain the overall direction that the particles were going, so using the direction that we created with the geometry, but we also want to add a little bit of noise just to create some more organic variation, and it's going to create a much more interesting effect. We also want to use a couple of force nodes over here, so I'll just drop a force. Let's see, pop force. And for this one, I will set the amplitude maybe to 4, and I'll leave the swirl size at 1, and just hold down Alt and drag this over to duplicate it. And this one will be a swirl size of 4. So we have a large noise and a smaller noise, and this will all add up to a much more interesting effect. Okay, and I'll also go up a level, and for my PubNet, I will go to the cache tab over here, and I'll just set the cache memory to maybe 50 gigs. And this will depend on how much RAM your computer has. So in my case, I can go all the way up to 128, but you know, it will depend on how many gigabytes of RAM you have. So I'll just set this to 50,000, which is 50 gigs. And now I can, so when I preview the cache, I can store a little bit more on the timeline, so I don't have to recache or resim every time. Okay, so one other thing that I would like to create here as well for the motion is, if we take a look at the current motion, we can see that the particles are sticking to the geometry, but I don't really want them to stick so uniformly to the geometry. I want to sort of have like a 3D feel to it. So I want some particles to be able to move further away from the geometry, and this will create a more dynamic effect. So what I mean by this is, if I go in my PubVof, which is sticking to surface, and go back here, let's just make some room over here. This is the new position that we generate, right? And if I plug the old position in this channel over here, so if I output the same position that we had initially, we can see that we don't have any of the sticking happening. Okay, and we can mix these values now by using a mix node. And I want the first value to be, so the first input will be our new position that we generate, and the second input will be the old, or rather the original position that we already had. So if I plug this in now, and I leave this bias at 0.5, we can see that we create a blend between these values now. So now some particles will also step further away from the geometry, and it will just create an overall more interesting silhouette. So hopefully you can notice that some of these particles are being allowed to go further outside of the geometry. So if I set this bias maybe back to 1, you can kind of see how this updates over here. And if I set this back to 0, this is now they're completely sticking to the geometry, and somewhere in the middle they are allowed to sort of branch further out. Okay, and we can go back. So this will be our initial movement of the particles, and I can go ahead and grab all of these 4 nodes, press Shift O, and let's just keep this nice and organized, and I'll name this to initial movement. So now that we have this initial movement of the particles, let's try to see if we can make these particles stick to the deformed geometry, or the animated geometry rather. So let's go up a level, and this will be a post-process effect. So what I mean by this is that we are gonna simulate the particles and then move them, sort of force them into position after they're simulated, and we will just create an attribute VOP over here that's plugged into the PubNet, and this will be my stick to animation. Okay, We will use the same technique with XYZ distance that we used earlier, and we will go ahead and let's drag this over a bit, and we will use this frozen geo and plug this into our second input over here. So now inside this attribute VOP I can access this frozen geometry from my second input, which is this one over here. And let's go ahead and drop an XYZDist. And from the pose, I want to generate it from the position of the points. And I want this to look at my second input, which is our frozen geometry. So we will again grab a primitive attribute and hook up the prim and the UV to this primitive attribute. And what we want to grab from our surface geometry, so from our frozen geometry, will be the P attribute. Okay, and if we plug this into the P output over here, now we essentially, and I think I messed something up. Let's take a look. Alright, so we also need the file so the primitive will look at the same frozen geo file. Okay, and now we essentially sticked the particles to our frozen geometry. So if we play this back, because we already made the particles stick to the geometry inside our simulation, this won't make much difference, as you can see if I turn this on and off. But this is an important step for the next part, which will be to use the actual animation, and I'll plug this into our third input in this attribute VOP. And instead of grabbing the P attribute from the frozen geometry, we will grab it from the deforming geometry. So if I switch this file, so this primitive attribute node over here, to look at my third input, which is the deforming geometry, now we can see that if I play back this animation, now this nicely sticks to our deforming object. So essentially what we're doing here is we are telling the points to look at the frozen geometry. So if I template this, look at this frozen geometry and find the nearest primitive and the UV coordinates for that primitive on the frozen geometry, and then use that primitive number and the UV coordinates for that primitive that it found, and then transfer it over to the deforming geometry, which is this one, this other one. Alright, and grab the P attribute from there, and then set the point to that P attribute. So for example, if I set the render flag to my frozen geo, and let's untemplate this, we can see that all of these primitives have a certain number. So in this case, for this primitive over here, it's 4900 and whatever. We are telling the points, and I'll template these points. Let's take a look, and maybe just make these points again. Alright, so we are telling the points, look at the frozen geometry and find me the nearest primitive, alright, which is this number over here, and also find exactly where on this primitive the point will land. So this will be the UV coordinates, and store this information, so the primitive and the prim UV, except now transfer it over to our deforming geometry and use the attribute, the P attribute from the deforming geometry. So hopefully this makes sense, and I'll also leave a link to an article that also explains this technique, and maybe you can have a better understanding by reading the article. But to reiterate, inside this attribute VOP, and I'll just set this to pixels, inside the attribute VOP, we are using the XYZDist to find the primitive number and the prim UV values from the frozen geometry, and then we are using these values to find the position attribute for our third geometry, which is the deforming one, and then we are simply setting the point position to be this value over here. And as a result, we have the sticking to the deforming surface. One other thing to note here is Now, since these particles are stuck to the deforming geometry, they are right on the surface, and we are sort of losing that nice silhouette effect that we created. If you remember in our PopNet, in this stick to surface, we can remember that we did this mix thing that sort of helped push some of the particles more outwards than others, and it created a very nice outline for the effect. And if I go to maybe frame 90, we can take a look and we can see that by turning this on and off, that if we have this off, then the silhouette is just a little bit more dynamic. So if you take a close look at the outline of our particles, we can see that this is moving more organically, and when I have this turn on, so the sticking to the surface, now we can see that this is very static. So we want to bring some of that original dynamic effect that we created back, and the way we can do this is we can simply push the particles outwards sort of by force if we grab the normal attribute from the frozen geometry. So we can step back inside this attribute VOP, and with another primitive UV I can just drag this over by holding Alt and duplicate this, and this will be, let's rename this to grab P, and this will be grab N. Right, so we will just grab the normal attribute from the geometry, and we also want to normalize this just so it's nice and consistent along the whole geometry. And if we simply drop an add node here and we add this vector, we can see how this effect will now look. So now they are pushed apart 1 unit length along the normal of the geometry. Which is not exactly what we want. So for example, if I drop a multiply constant here, and you don't have to add this node, this is for demonstration. If I drop this here and I can rescale this, we can see that we need to multiply this normalized value by a value that is going to be the distance from the point to the surface of the geometry, which luckily we have access to because XYZDist actually gives us this distance. So this is simply the distance from any point from our source to the closest point on the surface of the geometry. And all of that is to say that we simply have to use this normalized value and multiply this by the distance. Okay, and let's untemplate this. And we can actually see it over here in effect. So this is our templated geometry, and we can see that some of these points now are allowed to move forward further outwards from the surface of the geometry, and this will create a much more interesting silhouette or outline. And actually I forgot to do something here, and if I go back inside this attribute VOP, we can see that this grab N, we said that we're going to use this to grab the normal attribute from the geometry, but we just left this as P. So here we have to type N, so that's capital N, hit enter, and now we're getting the accurate result. So we can see our geometry, or rather our outline is having a nice dynamic effect.